Hi, my name is Zach Ranieri. I, along with Daniel Wiseman, are the co-founders of Jabberwocky. Jabberwocky is a highly performant indexless database. The purpose of this video today is just to showcase some of the performance that Jabberwocky will have to offer its users in the future. To get started, I'm going to start up our server. This is a cloud-hosted server on the East Coast. What's happening here is that we have a data set from the public site Kaggle. It's the data set from a company called Nearby. They're a social media company, so it's all their social media posts over the course of 10 years. The data set's roughly 44 gigs in size. It has 169 million rows of 9 columns in each row. What we're doing is that we've started up a fresh instance of Jabberwocky. This has no previous configuration. It's a completely bare instance, as all Jabberwocky instances are. And we're going through the CSV file line by line and adding in each item in every row and the relationships needed between them. It's important to note here that this isn't, we're not doing some kind of special process here. This isn't a particular, we're not converting it to, like a data or storage syntax ahead of time, anything like that. We're running each line and we're running it in the same endpoints that every front-end query comes through does. The reason that I have this on server and I don't have it on my local connection is that I really wanted to use this as a performance test of Jabberwocky as a database, not of my local internet connection or anything in between. What this is logging here is, as it goes, it's logging the total number of items processed so far, how many items per second, so roughly 19 million to 20 million here, and then how much time has elapsed. Now, that's going to go through. It's going to take roughly 3 minutes to complete all 1.5 billion items. While it's doing that, we'll go ahead and type out our query syntax just to show you that even though we're indexless, we're actually still much more performant than most other options out there. So here I've started up a new space. Spaces in Jabberwocky are effectively sub-databases within your database. So you can have multiple sub-databases, and they're pretty much isolated environments. Here I've declared what types of data we have. So we have these numeric items and we have these string items. We also have the availability to declare Boolean items, but I don't need that here. This is the only configuration you need. You don't have to decide relationships between them or anything else. You just simply have to say what you have and what type of data it is. So let's go ahead and we'll start to type out a query here. Do a search. And we'll get the first 10 items. So we want post text. So you'll see here that we are fully typed. So it is able to, at least here in TypeScript, able to tell me what I've done. And this is based on what we declared up here. If I go ahead and I swap out to numeric, you'll notice that it's able to fill in the blank and let us know. So what I want actually is post text. Perfect. Now this data, it isn't normalized. And what that means is that the post items are, they'll be any casing. They're not lowercase, uppercase. And I really want to search for all items that contain coffee, but I want to make sure that they contain any case. I don't want to have to look for different variations. I want uppercase, lowercase, and everything in between. And then we'll just add a simple display option here so we can go ahead and see the results. All right, perfect. Now we can also see that the database has finished. It ran 1.5 billion items in roughly 190 seconds. It was running at about 8 million items per second. You will notice a time difference here. You'll notice how it's quite a big difference. The reason is at the end of a large data set like this, we have to run some cleanup scripts, some restructuring, some things like that. And I wanted to make sure that all of that time is included in this benchmark. So the full time it takes to process all of that is included. So 1.5 billion items, 190 seconds, 8 million items per second. Here what we're doing is we're logging the data size. So this was the original data set, 43.09 gig. In the database, it takes up 82.3 gig, and that's a data multiple of 1.9. So what I mean by data multiple is anytime you add, you have to upload your data into any database. Just from the database's structure to all the indexes it needs to maintain efficiencies, this increases your data size. So it's not uncommon to see data multiples of 10 to 15 x what your original data size was, just depending on what that database and what you need for query efficiency. So here you can see that we're only 1.9 times your original data size. If you were to do a data syntax like JSON, we'd actually be smaller than its JSON representative. And we get this through, this is a big benefit of not having to have indexes to maintain query performance, is that we see a much higher ability for data efficiency. So let's go ahead and just to showcase that we aren't losing any performance. What this is going to do is just compile my TypeScript here, and then it's going to run it, and we'll export or we'll log the query time. So perfect. We got 10 items, 10 posts that contain coffee. And then if we go down here, we'll see that it took 3.9 milliseconds. So that's logging the moment that the server received the request, the parsing of the request, running it through the database, to the moment that it returns back the response. So this is complete server time, so it takes about 3.9 milliseconds. So let's try something else. Let's do uppercase. Let's do all posts that when uppercase contain hi, for instance. If we go ahead and log this, we'll compile our TypeScript. And fantastic. So there we actually only took 56 microseconds. That's the interval below a millisecond. And you can see it's matching everywhere that we have HI and anything. So this one might not be as useful of a query, but it showcases that we are able to match, utilize string text transformations, do a more intensive match by looking within strings themselves, and then return back in an extremely performant manner. And that's for the most part what I have today. I appreciate you for your time. If you have any questions, please feel free to leave them below, and I'd love to get back to them. Thank you.